titled Learning Hybrid Models for Variable Impedance Control of Changing Contact Manipulation Tasks. In this paper, we look into robots performing manipulation tasks, which can be considered to be execution of a desired trajectory, which is provided to the robot either in terms of a demonstration from an expert or in terms of kinematic plan by a planner. We assume that a valid kinematic plan is available, and we look into how to deal with the dynamics during the task execution. The different interaction forces that the robot experiences during the task will result in different acceleration and can affect the motion of the robot. These changes in dynamics could be continuous, which can be due to the friction, viscosity or elasticity during the interaction, or it can be discretely changing, which can be because the robot makes or breaks a contact with the environment, or it can be due to sudden and discontinuous changes in environmental attributes. For example, on the left hand side, we have two simplified examples of continuously changing dynamics. In the first, the robot is pulling a spring system and moving along a predefined trajectory. Because of the elastic nature of the springs, the robot is experiencing different forces as it moves along the trajectory. In the second, the robot is also in continuous contact, but the environment damping is continuously increased, which causes the robot to experience different forces as it executes this task. On the right hand side, the right hand side shows examples of discrete changes in dynamics. This can be because the robot makes contact with a new surface as on the top, and depending on the type of contact that it makes, for example surface contact or edge contact, the interaction dynamics is different. At the bottom, the dynamics is discretely changing because the robot moves from a surface of a higher friction to one of a lower friction. Here, the environment is discretely changing, which causes the robot to experience a different frictional force. Here, it can be seen that the robot, as it performs the task, it overshoots when it moves to a surface of smoother friction. In general, changing contact manipulation tasks can be seen as a piecewise continuous system where the dynamics is continuous within a contact mode, but it is discontinuous at the transition point. At the transition point, the robot may not be able to use the same model that it has for the previous model. Therefore, one way to approach such piecewise continuous system is by learning a hybrid model that learns separate models for these discrete modes and has a higher level transition model that is able to identify which mode the robot is in. Before introducing the hybrid framework that we have, the performance task being considered here is, we assume that the robot has the desired motion trajectory from a planner, and the robot should be able to produce the control signal which will enable it to execute the task while dealing with the changing dynamics during the task execution. In a baseline case where with no learning, the robot will have constant P and D gains for the PD controller, which will, as shown previously, which will not enable the robot to complete the task successfully. The robot experiences the world and the environment using the end effector force torque sensor, as well as using the current end effector force and velocity. We propose a hybrid learning framework which has a higher level transition model which tries to identify the current mode that the robot is in, and each of these modes is associated with a dynamics model, an adaptive control law, and a relevance condition which determines when the mode is relevant and should be applied. The dynamics model and the adaptive control law is incrementally and continuously adapted, and because of this, it provides an online learning framework which enables the robot to learn new modes, identify new modes, and learn the dynamics model for that mode as the task is executed. For learning the dynamics of a mode when the robot is within a contact mode, we use the incremental variant of GMM. GMM is used to predict the end effector forces and torques given the previous measurements of the end effector forces, torques, and the velocity. The forward model then is able to predict the end effector forces and torques that can be expected during the task execution in that mode. We also have a PD controller here as described previously, but instead of having constant P and D gains, we vary the controller gains, and for doing this, error in prediction of the forward model as a way to adapt the PD controller gains, as well as to provide a weighting term for the predictions given by the forward model. The idea here is that if the forward model is accurate, if the predictions are good enough, then we weight the feed-forward term with a higher weightage. However, if the predictions are not accurate, we use a higher PD gain and follow the provided trajectory more accurately. This way, the robot is able to use the forward model and complete the task with lower impedance gains when the forward model is accurate. This is the controller formulated in mathematical terms. The first part of the controller is the PD controller, where the P and D gains are continuously changed depending on the predictions given by the forward model in that mode. The second part is the force control part, which is used to apply a desired force in a direction that is orthogonal to the direction of motion. And the final part is the feed-forward term that is provided by the forward model. The transition model is a higher level model that tries to identify which mode that the robot is in currently. And for doing this, we represent each mode using a meta representation that is then used for incrementally clustering into different clusters using the algorithm called BERT. We use a feature representation for this clustering that makes it robust to motion direction and applied normal force. The features are chosen such that the framework will be able to distinguish between these modes, and because of this, it is dependent on the type of task that you want to do. So if the robot has to differentiate between surfaces of different friction, we use this ratio, which is the ratio of the frictional force over the applied normal force. Theoretically, this gives the ratio for the coefficient of friction for the surface, and because of this, it is able to identify between the two surfaces in this figure. Similarly, for identifying the different type of contact that the robot makes with the surface here, we also incorporate the ratio between the torque and the applied normal force. Because of the representation that we use, the framework is able to identify between the modes while being robust to the direction of motion and the applied normal force. With the transition model and the lower level models, we have an adaptation mechanism that is as follows. If a mode change is detected, and mode changes can be detected using sudden and pronounced changes in the sensor measurements of force torque sensor. If a mode change is detected, then the robot uses a high stiffness control strategy and tries to identify the mode that it is in. If the mode is identified, then it uses the dynamics model for that particular mode and applies the variable impedance control as described previously. If the transition model is unable to identify the mode, then it labels it as a new mode and learns a dynamics model for that particular mode, which can then be used for subsequent operations. We wanted to test the following three hypotheses experimentally. We wanted to make sure that learning separate dynamics model for different modes is better than having a single global model. We also wanted to make sure that the framework is able to provide efficient and reliable performance for changing contact tasks. Finally, we wanted to test if the feature representation that we use is able to make the identification of modes robust to changes in the direction of motion as well as the applied normal force. We want to minimize the error in motion tracking during task execution, as well as minimize the time taken to detect the mode, while maximizing the accuracy of the predictions given by the forward model. In this video, we show an example of the framework in action. In the first video, the robot is provided with the model for the first surface, but not for the second surface. And we want to show that because of this, the robot overshoots and is not able to complete the task successfully. Here, the robot is learning from scratch. It is able to identify that a mode change is detected, and it goes to high stiffness and classifies it as a new mode and learns a dynamics model for that mode. Here it can be seen that when a mode change is detected, the robot briefly goes to a high stiffness state, and then once the mode is identified, it switches back to a lower variable impedance control. Here the robot sees a new surface, surface 3, and learns a dynamic model for that mode. But when it sees a previously identified surface, then it uses the dynamics model that it has already built and improves upon. In the second plot here, it can be seen that the trajectory tracking accuracy, the error in trajectory tracking spikes when there is a mode switch, but then it goes back again when it identifies the mode and applies the variable impedance control. At the bottom, it can be seen that the robot is able to identify the mode with the current mode accurately with the highest confidence in all cases. In this task, the robot performs the sliding motion, but while using different types of contact, while making different types of contact with the surface. It is learning the dynamics for each of these modes separately online. The learning is then tested for the robot performing the same task but in different sequence and in a different direction. It can be seen that the robot is still able to identify the modes correctly. It can also be seen that the feed-forward prediction is 0 when the robot is trying to identify the mode, but then it uses the forward model for predicting the forces when it has identified the mode. It can also be seen that the prediction is very close to the actual measurement from the sensor. Here, the robot is performing the same task, but while applying a higher force than the one it learned the mode for. So here it is applying twice as much force as it applied previously, and it can be seen that it's still able to identify the modes. At the bottom, it can also be seen that the robot briefly uses a high stiffness control strategy while it is trying to detect the mode, and once it has detected, it switches to the variable impedance mode control. The advantages of this formulation of hybrid learning framework is that you do not need to explicitly model the environment dynamics. It can also learn new modes when it observes previously unseen mode. And the learning is completely online and happens continuously, which enables it to handle smooth as well as discontinuous changes in dynamics. And the framework does not learn a sequence of mode, and because of that, it is able to identify the mode regardless of the order in which they appear. The state representation we use also makes it invariant to the direction of motion as well as the applied normal force. So, in conclusion, we presented a hybrid framework which learns the piecewise continuous dynamics, which is the characteristic of changing contact manipulation task. We have a higher level transition model that identifies the mode that the robot is in currently. It is also able to label a new mode if it has not seen it previously. Then we have a lower level dynamics model for each mode, which is also continuously and incrementally adaptive, and it is able to predict the end effector forces and torques within that mode. We have a adaptive variable impedance controller, which is used to complete the task, execute the task while minimizing the error in trajectory tracking. We plan to incorporate a contact anticipation model for this framework. Currently, the framework is not able to predict a contact mode or when a robot will make a new contact. If the robot is able to predict when the contact change might occur, then it can be used to modify the controller so that it provides a smoother transition between these contact modes, and it provides safer interaction when a new contact is made. Thank you very much for listening. I'm happy to answer any questions you have. Also, please feel free to post your questions in the Slack channel. Thank you.
All right, thank you, Saif. We have a few questions from the Slack channel. I'll start with Matt's from Park. He asks, if there was a continuous degradation, e.g. maybe the block gets smoother over time, reducing the amount of friction, would the system just decide it is a new mode after some degree of degradation? If so, then the new learned mode model would have a lot of overlap with the previous one.
Yes, so I assume, can you hear me?
Yep.
Yeah, okay. So if the degradation is smooth, then the way we have currently formulated the framework, it will just adapt to the current mode that it has because it's incrementally adapting the model for that particular mode. But yes, if it degrades to a level where the friction matches a different mode, then yes, there might be an overlap. But in that case, it may not really matter which of these modes the robot identifies it as, because as long as the predictions for the mode is accurate, then the robot is able to continue the task with the desired variable impedance behavior.
Okay, thank you. I think this is probably a related question, though it's from Pat Langley. Does your approach only revise parameters, or does it consider new functional forms, i.e., is it doing class system identification or structural system identification?
Currently, we are just adapting the model, the parameters of the model. So in this case, we have the incremental GMM and the adaptive variable impedance control, but I think we could incorporate different functional forms for the different modes, but that's not something that we are currently doing.
Okay, thank you. Question from Shawali from Park. She says, very cool work. I didn't understand the motivation between switching between PD control and trajectory based. Could you please elaborate on that?
So I assume what she meant is when a new mode is identified, why we choose constant stiffness, the high stiffness controller, before switching to the variable impedance. If that is a question, the reason we use the high stiffness currently is because when a mode change is detected, we want the mode identification to use measurements from the sensor that are as clean as possible. And we found that when the robot uses a high stiffness precise control, that's when the measurement from the post-hoc sensor is most reliable. And it's able to identify the mode better. And after it's identified the mode, then you can choose the controller that would suit better.
Okay, and then she had a part B to her question. So she then said, can this learning be integrated with typical cognitive systems / planning systems, hierarchy of tasks and actions? Also, does the work explicitly encode something akin to preconditions, effects, etc.?
Yes, I mean, conceptually, I think it is possible to incorporate this because we still have this hybrid system. But I don't know how exactly I would do it at the moment, but yes, it should be, at least theoretically, it should be possible.
Very interesting. Pat has another question, Pat Langley. Does your system produce something like a finite state machine that stores transitions between states, or are the states implicit?
So I'm not sure the question is clear.
Do you want me to, maybe I'll state it again. Pat's just clarified and said, are the transitions implicit? So I'll start from again. I'll start from the beginning. Does your system produce something like a finite state machine that stores transitions between states, or are the transitions implicit?
Yes, the transitions are implicit. We have this feature representation that helps the identification of a particular mode. And because of that, the transition is, I think it is implicit. It can be said to be.
Great, thank you. So we're at